Hello everybody, thank you for watching this presentation of IEEE RoboSoft 2020 conference. This work has been carried out by researchers from the University of Castilla-La Mancha, Spain. Our work is about a McKibben muscle based on a hydrogel material that can self-heal without external agents or stimuli. We're starting with a brief introduction. As you know, from the beginning, robots have been often inspired by nature. Even traditional industrial robots are inspired in the human anatomy. So, a fortiori, soft robots do. Our body is plenty of muscles that can contract and make forces to move our own skeleton. For years, robotic engineers have taken this idea to create soft linear muscles. Here you can see a couple of examples of soft linear artificial muscles. Commonly, these muscles are actuated pneumatically with pressurized gas, which brings up the acronym PAM, Pneumatic Artificial Muscle. In fact, this work is based on the McKibben muscle, a kind of PAM. As you may know, this McKibben type muscle can be easily manufactured and consists of an inflatable inner bladder usually made of an elastomeric material inside a braided mesh sleeve. The behavior of this muscle is simple, as it can be seen here. When the bladder is inflated, it tries to expand omnidirectionally, like a balloon. However, thanks to the mesh, this expansion is restricted. The mesh can only increase its diameter by changing the braiding angle, leading to a contraction in the muscle, something similar to the scissor mechanism, where the contraction is achieved thanks to a change in the angles between the bars. The contraction in the muscle leads to a force if something or someone is pulling the muscle. In fact, the force and the contraction are paired for a certain pressure. That's why these muscles are characterized with force contraction curves at a constant pressure. When the muscle movement is free, it contracts to the maximum, but no force is exerted. However, if someone or something pulls the muscle with a force, the contraction is lower. If this action blocks totally the muscle at its initial length, then the muscle exerts the maximum force. Doing these four different values of pressure, the muscle is fully characterized. Of course, the higher the pressure, the higher the force or contraction. So, this kind of muscle works properly like it has to. But what if the bladder gets damaged? If there's a leakage in the bladder, the muscle will not work properly. This is one of the biggest problems in pneumatic artificial muscles, and the reason why the search for self-healing materials is becoming one of the most active research lines in soft robotics. A polymer capable of self-healing can be used instead of simple elastomers to build these actuators, so that they can self-repair when they get damaged with punctures, cuts, or tears. There are a lot of polymers with self-healing abilities. Many of them can self-heal by means of heat, others by means of light, pressure, water, by adding external agents, etc. We can also find some cases of self-healing materials in soft robots. For example, the work shown here, in which Torin et al. Developed different pneumatic actuators using an elastomer capable of self-healing by applying heat. Following the search for new materials, we are currently working with hydrogels in soft robots. So we tried to develop a hydrogel able to self-heal without applying external stimuli, such as heat, light, and without adding any external agents. For those who are not very familiar with hydrogels, these materials are three-dimensional polymer networks capable of absorbing large amounts of water without losing their structural integrity. Prior to this work for RoboSoft 2020, we developed a hydrogel-based soft fingertip capable of changing its stiffness and volume under an electric field. We called this material CN hydrogel, as it is based on a cationic network with free negative ions that drag water when an electric field is applied, originating a gradient in the swelling degree that causes the changes in stiffness and volume. In fact, the swelling degree is probably the most important feature of hydrogels, as these materials can gain and lose large quantities of water. The water contained inside the hydrogel structure is quantified through the swelling degree, calculated as the weight of the sample minus the weight of the dry sample divided by the weight of the dry sample. So, freshly prepared, we obtain a hydrogel that we call native. If we add water to this native hydrogel, we obtain a new one with higher volume and swelling degree. However, if we leave the initial native sample under ambient conditions for 1 week, it loses water by evaporation, and we obtain a hydrogel that we call equilibrated. This means that the water inside its structure is in equilibrium with environment, so the hydrogel keeps its weight constant. To obtain a dry sample, an external heat should be applied. We analyzed the self-healing capabilities of our CN hydrogel in each of these states, obtaining great results in the equilibrated state. This study was performed following these steps. Firstly, non-damaged virgin hydrogels were cut into two different pieces. Then, these two pieces were aligned and put together. After 24 hours, without any external stimulus nor adding any agent, just leaving the pieces together under ambient conditions, the two pieces rejoined, becoming a unique material again, named healed sample. Lastly, these healed samples were stretched to obtain their mechanical properties and compare them with those of the virgin specimens. In this image, you can see the behavior of a healed specimen being stretched. Now you are watching images of the healed sample obtained by scanning electron microscopy. These images certifies the self-healing capabilities of our CN hydrogel in equilibrated state. Comparing the mechanical properties of the self-healed samples with the virgin ones, we obtain good results. In this graph, we show the tensile stress strain curve for a virgin specimen in blue and a healed one in red. It can be seen that the performance of the healed specimen is approximately equal to that of the virgin until the failure, which is the major difference between the two cases. The numerical results can be seen in this table. The Young's modulus is approximately equal in both cases, as you can see in the graph. This leads to an efficiency of 100% in Young's modulus. Higher differences are observed in the ultimate tensile strength and the strain to failure, as mentioned before. Taking into account the energy absorbed until 10% of strain, the efficiency is about 100%, as it can be seen here. Finally, considering the fracture toughness, the self-healing efficiency is 32%. This efficiency is obtained dividing the value for self-healed samples by the one for virgin samples. In other words, dividing the red area by the blue area in this case. The conclusion of all these results is that our self-healed hydrogel breaks earlier than a virgin specimen. However, until that point, the performance of our material is really good. And the most important thing, this self-healing doesn't need external stimuli nor agents, which motivates us the use of this material in soft robots. In particular, we developed a hydrogel-based McKibben muscle. Like the traditional McKibben muscle, ours consists of an inflatable inner bladder inside a braided mesh sleeve. The only difference is that our inner bladder is made of our equilibrated hydrogel. To manufacture this hydrogel bladder, we followed these steps. Firstly, the hydrogel solution is poured into a methacrylate tube. Then, a narrower tube is introduced inside the solution to form the cavity of the bladder. Finally, the solution is photopolymerized using a UV light lamp. Then, the bladder is removed from the methacrylate tubes and is left under ambient conditions for 1 week to reach the equilibrated states, like this one previously shown. Once built, the next step is to test and characterize the muscle. To do that, this setup was designed to record forces and displacements in the muscle using a material testing machine and its load cell. Furthermore, a pneumatic system was built to guarantee the supply of gas. This pneumatic system is formed by three serial components: a manual valve, a precision pressure regulator, and a solenoid valve controlled by an Arduino board. This system is responsible for providing the muscle with gas from the network. Having the hydrogel-based muscle and the stub, now we want to characterize these muscles and to prove the self-healing on them. So we established this methodology. First, the typical isobaric characterization for the virgin muscle is obtained. Then, the bladder is punctured and is left under ambient conditions during a specific time in which the self-healing process takes place. In this case, we consider 3 periods of time: 10 minutes, 2 hours, and 1 day. After that, a new isobaric characterization for the self-healed muscle is obtained. The results for the virgin muscle are shown in this graph, which proves that our muscle works properly like any other McKibben muscle. However, with this characterization, we didn't notice perceptible differences between a virgin muscle, a self-healed muscle, and a punctured one. The reason is that the gas lost through the puncture is lower than the one that can be supplied by the pneumatic system to guarantee the pressure inside the muscle bladder. The input compensates the losses, so we couldn't verify whether the muscles were healed or not. The solution was using the same previous test, but under a constant amount of gas inside the muscle, which is what we've called no-flow characterization. In this case, once the muscle is filled with gas, the supplier valve is closed, so there is no flow towards the muscle. We perform the test from the muscle initial length to the point where there is no force. And we repeat this several times. If the muscle is able to replicate its performance, it means that no gas is leaked. Otherwise, if there's a leakage, it would be noticed because the muscle would not work. Now we have this no-flow characterization for a virgin muscle. The gray dotted lines correspond to the isobaric characterization, as you are watching right now. Of course, with this no-flow procedure, the pressure inside the muscle is not constant, because we are disabling the system that guarantees that, working under a constant amount of gas. This is the no-flow characterization for a virgin muscle sample, and this is one for a self-healed sample. It's observed that the self-healed muscle replicates the virgin actuation up to a certain pressure, 0.1 megapascals in this case, corroborating the self-healing ability of our hydrogel. But in this case, it breaks at 0.12 megapascals, losing the gas contained inside. Thanks to this no-flow characterization, we can observe clearly when the muscle fails. Repeating these tests over several muscles and considering the different self-healing periods, we can analyze the breaking pressures. In this graph, you can see the results. Even after 10 minutes, our muscle can support 0.1 megapascals on average, which is a reasonably high value for the short time considered. It means that only after 10 minutes, this self-healed muscle can lift 5 kilograms, contracting the 5% of its initial length, for example. Of course, this breaking pressure increases as it does the self-healing time, reaching 0.15 megapascals after 1 day, which is a really good value. To sum up, we have used our hydrogel to build a McKibben muscle which benefits from the self-healing capabilities of this hydrogel. After being damaged, the muscle can perform properly, as you are watching right now, even after only 10 minutes, thanks to the self-healing without any external agent or stimulus. And that was all. Thank you for your attention.